Chapter 7 and 8, Section 2 and Part 2. Let's have the second method for testing the uniformity, which is a chi-square test. So in this method, in chi-square test, we divide the interval of 0, 1 to n classes, or let's say n intervals. Okay, and then we set EI to be the expected number of samples to appear in ith class. So yeah, I mean, let's say we are dividing the interval of 0 to 1 to 10 intervals, 0.0 to 0.1, 0.1 to 0.2, and so on. Okay, so we have 10 classes or 10 sub-intervals. So what's our expectation to have about the number of samples appearing to each in each interval, EI? Shouldn't this be n divided by little n? Yeah, this large n is the sample size, so we have large n numbers, and the little n is the number of intervals, the number of classes. So if they are based on uniform distribution, so this is our expectation, to see the same amount of numbers in intervals, right? So then let OI be our observed number of samples appearing in ith class, and then by having EI and OI, we can calculate the chi statistics by this equation. Okay, and then by having a significance level alpha, and also assuming n minus 1, n here is the number of classes or intervals, so n minus 1 will be our degrees of freedom for chi-square distribution. So we go to its table and obtain the critical value of chi-square with alpha and n minus 1. Okay, so here is our conclusion. If the calculated chi statistics is greater than the critical value, then we reject null hypothesis. Okay, but if it's less than or equal to the critical value, then we fail to reject the null hypothesis. Okay, so this is the chi-square test. And here is the table for the chi-square distribution, so we can obtain the critical values by assuming the alpha values. As you see here, we have these alpha values, and also the degrees of freedom, which is n minus 1. Okay, so this column, the degrees of freedom, is n minus 1, and here we have the alphas, right? So by having, oh sorry, it's n minus 1. Yeah, n minus 1, and yeah, by having the alpha values here and the n minus 1 as the degrees of freedom, we can obtain the critical value from this table. Okay, so as a discussion for the frequency test on chi-square test, we need to choose n such that EI be greater than or equal to 5. So this means let's say the chi-square test will be valid for a sample of random numbers, which includes at least 50 random numbers, right? So yeah, you see here the chi-square is valid and appropriate for somehow a large size sample, but the KS method, the Kolmogorov-Smirnov method, can be applied for the small size samples as well. So in general, we can say the Kolmogorov-Smirnov or KS test is more powerful than the chi-square, and so it's recommended. Okay. So after having two methods for testing the uniformity, let's have the test method for correlation, which here we call it as a test for autocorrelation. Okay, so here we check the dependencies between the numbers in the sequence. So we have a sequence of random numbers, right? Rn R1 to Rn. So we want to see if there is any correlation between these random numbers. Okay, and here we consider a lag, and also the starting point, which is ith number. So we start from the ith number, and then we jump to to the next number, which will be with a lag of L, and then we will consider those subsequent numbers to be tested for other correlation. For example, in this example, in this table here, we have 30 random numbers. If we start from the fifth random number, and if we assume the lag of 5, okay, so L equals 5, so we will have these subsequent random numbers, a random number of 5, 10, 15, 20, 25, and 30. So we have 6 subsequent numbers, and we will see if there is any dependency between these 6 numbers or not. Okay, so here the other correlation rho IL, as I said, will be investigated for those subsequent random numbers, which will be Ri plus L. So for our example, I equals 5 and L equals 5 as well, right? So we have with this relation here, we have R5, and then R5 plus 5 will be R10, right? And then R5 plus 2 times 5 will be 15, and then 20, and then 25, and 30 at the end. Okay, so yeah, so here we have, as you see here, we have 6 subsequent numbers, and we will check the dependency between these 6 numbers by the method that we have here. Okay, and the value of m here, so see here it goes to I plus m plus 1 times L. So the value of m should be obtained here by a way that we have I plus m plus 1 times L should be less than or equal to n. Okay, so we obtain the value of m here such that we have this inequality. Okay, and the length of the subsequent numbers that we will test for dependency will be m plus 2 numbers, right? Because we have m plus 1 numbers here and also 1 number as the ith number. So in total, we will have m plus 2 subsequent numbers for testing. Okay. A non-zero autocorrelation for any subsequent numbers will be considered as a lack of independence. Okay, so here we have a two-tailed test for the correlation between the numbers. H0, or the null hypothesis, is rho IL equals 0, and H1 is against the null hypothesis. Okay, so for large values of m, if we have a large sample of random numbers, then m will be large as well, right? And then the estimator of the rho IL, which we call it as rho hat IL, is approximately normal if the values of subsequent numbers are uncorrelated, right? So as you see here, it will be based on normal distribution if the subsequent numbers are uncorrelated. Okay, so based on this property, or let's say assumption here, the test statistic is this: Z0 equals rho hat IL, the estimator of the other correlation, divided by the sigma of that other estimator of other correlation. So Since it's based on the normal distribution with the mean of 0, then if it divides that random variable by its standard deviation, and since it was based on a normal distribution, then Z0 will be a standard normal distribution with mean of 0 and variance of 1. Okay, so yeah, by having this, then we will get, actually, because we have our statistic here, which is this Z0, and we know that its distribution is based on a standard normal distribution, so we can obtain the critical values for any alpha, and we have the Z0, so we can check if we can reject or we can accept the null hypothesis here. Okay. So our test statistic here is that 0 and rho hat IL and sigma rho hat IL can be calculated by these two equations here. And so for any alpha, we will have this range. If Z0 lies in the range of minus Z half alpha and plus Z half alpha, then we fail to reject the null hypothesis. Okay, so for our example here, as you see, I is 5, L, the lag is 5 as well, and the M is 4, right? So the rho hat IL becomes this 1 over M plus 1, 4 plus 1. Then summation over K going from 0 to M, Ri, which is R5, so it's 0.89 times Ri plus K plus 1 times L becomes R10, 0.93, okay, and plus 0.93 times 0.91 and so on. At the end, we have 0.95 times 0.87, okay. So this minus 0.21, it becomes 0.57746, okay. And the sigma rho hat IL is this. So we have here 13 times 4 plus 7 divided by 12, 4 plus 1, okay, and it becomes 0.1280. So by having these two values, Z0 becomes 4.511. Now, if we assume that alpha is 0.05, okay, then the Z half alpha, which is Z 0.025, from the standard normal distribution table, we can obtain this number. It will be 1.96, right? So as you see here, 1.96, Z0, which is 4.511, and 1.96. So as you see here, the Z0 doesn't lie in this interval, so here we say reject the null hypothesis. Okay, H0, reject H0. So yeah, here we can say that the sequence of random numbers are independent. Okay, so we can continue that example for these numbers, starting from the third number 0.23, and also having the lag of 5. Okay, so you may try this by your own, and if you have any question, we can complete this example in our live session. Okay, thank you.